Hello guys, welcome to lecture 3 of power circuit and electromechanics. Okay, in this lecture we will study transformer. First, introduction. The transformer is the equipment we use to transfer electrical energy from one circuit to another circuit through time varying magnetic field. We can apply them in both power and communications. In power, we are using the transformer in transmission, distribution, and utilization of electrical energy. We are using step up or step down voltage transformer at a fixed frequency, 50 or 60 Hz. The power level is from 100 watts to hundreds of megawatt. In communication, we use transformer for impedance matching, DC isolation, and changing voltage levels at a power of a few watts over a very wide range of frequency. This course only talk about power transformer, but before we go into power transformer, I will introduce some transformer in communication too. So first we talk about ideal transformer. Let's consider a magnetic core here with two coils. We have here a magnetic core and we have coil 1 and coil 2. Assuming we ignore losses, rate capacitance, and also leakage flux. Okay. Also, the magnetic permeability of the core is infinity, or in other words, we have zero reluctance of the core, and therefore we can write the first equation for coil 1, Vt equal N1 d phi by dt. It's the same phi going through both coil. So on coil 2 we can have V2, which is d lambda 2 by dt, and will be calculated by this expression. Now both are varying with time, but if you calculate the ratio between V1 and V2, you will end up with a constant N1 divided by N2, and we call it turn ratio A. Now if we calculate the total MMF and using the right hand rule, we can finally find out that the MMF equal N1I1 plus N2I2 will be 0 because the reluctance R is 0, and therefore we can calculate the ratio between I1 and I2 here, and it's still another constant, which is minus 1 over A, if we define N1 divided by N2 is A, turn ratio. Okay, so mathematically we can form an equivalent circuit like the top picture here. Okay, however, it's not physical because here we have energy coming in from both coil, and we don't have anything consuming energy here. So a closer to the physical system, okay, would be the second equivalent circuit here, where you have the current coming in coil 1 and will be going out coil 2. So it means we are supplying energy to coil 1, and then we provide the energy to a load on coil 2. For coupling coefficient, we can prove that the coupling coefficient equal 1 and therefore we finally can establish that L1 N2 square will be equal to L2 N1 square. Okay, this is important when we try to use this to change the impedance or to have a different inductance, self-inductance. Now we are looking at the impedance changing property of an ideal transformer. Consider an ideal transformer with the new convention model, the new model using the physical convention. Okay, so you are applying a load with an impedance of RL. It can be ZL, but right now we just call it RL. Okay, and on coil 1 we are supplying a current I1, and the turn is N1 on coil 1 and 2 on coil 2. Okay, by Ohm's law, for this load we can easily write V2 divided by I2 will be that RL. And remember, for this transformer we have V2 equal V1 divided by A. If you switch back here, that's V1 divided by V2 equal A. So V2 should be V1 divided by A. Okay. So, and also I1 will be equal A time of I2 equal A time of I1, as you can prove it from the previous slide. Okay. So now if we try to calculate the equivalent impedance here by dividing V1 by I1, we'll take this V1 divided by I1. Okay, so we will end up with this A square RL, which is N1 divided by N2 square RL here. We can further extend this to a complex load because we are using AC power, AC current. The current is varying with the frequency. Now it's interesting that by looking at this, we see that if we put RL here on coil 2, it will be equivalent to putting N1 divided by N2 square RL, a value of that, right on the first, across the first coil terminal here. So we say the load RL on coil 2 is now being referred, okay, being converted into A square RL on coil 1. Similarly, an impedance ZL on coil 2 here will be converted into A square ZL on coil 1. So that is called impedance changing property of ideal transformer, and we can use that, okay, we can use that property to do the impedance matching. Okay, the problem here is we have an energy source with an internal impedance of Z nuff, and our load will have the impedance of ZL. In order to maximize the power or energy transfer from the source to the load impedance ZL, we should have a matching situation, meaning ZL would have the same magnitude as Z nuff. However, in practice, they are not the same. Okay, so we can fix that problem by using an a transformer. So we put a transformer between the source and the load ZL, and then we can convert that ZL into A square ZL, and we can change the turn ratio so that the converted impedance would be the same or similar with Z enough, and then we will have the maximized power transfer. So example 3.7 will show you a situation where we need that property. Okay, so we need to find the R in between so that the load resistance will get the maximum power on it, and we finally can find R equal 13.5 ohm. Be careful that the text in the books has some error, so we need to use the information I have on the slide here. So this is the end of part 1.